Hello everyone, myself Dr. Ranjith Kumar Gatla, working as an Associate Professor in the Department of Electrical and Electronics Engineering, Institute of Aeronautical Engineering. So in today's class, we are going to discuss some numerical problems on maximum power transfer theorem. So already we have discussed what is the statement of the maximum power transfer theorem and what is the procedure to apply the maximum power transfer theorem to find the maximum power flowing through a particular load resistance. So here, first let us go with problem 1. So in this problem, find the value of the R in the circuit shown in figure such that the maximum power transfer takes place, and also we need to find what is the amount of power that is transferred through the load resistance R. So here, according to the maximum power transfer theorem, so when R is equal to the R Thevenins, so at that particular condition, the maximum power will flow through that particular load resistance. So here, what are the two things that we need to find? First, we have to find the load resistance R value. So to find the load resistance R value, first we need to find the R Thevenin's value, because where R is equal to R Thevenin's, at that particular condition, the maximum power will flow through the the load resistance. So already the condition that they have given is the maximum power is transfer takes place. So which means, so the condition for the maximum power takes place is R is equal to R Thevenin's. And the maximum power that is taken place here, it is V, the P maximum, and the maximum power that we need to find is VOC square by 4 into R. So here VOC is the Thevenin's voltage and here R is the load resistance that we are going to find, right? So which means to find the maximum, the amount of that power, so here we need to find the VOC also. So and the condition for the maximum power is condition for P maximum, which is R is equal to R Thevenin's. So which means here we need to find the R Thevenin's value and VOC value. So VOC is nothing but V Thevenin's or open circuit voltage, and R Thevenin's means the open circuit the equivalent resistance across the load terminals, right? So first let us find the V Thevenin's. So the procedure to find the V Thevenin's here it is, first we should know where we should find the V Thevenin's, so that we already know. So across the load terminals we should find the V Thevenin's or VOC. So which means we have to replace the load resistor, okay, the load resistance as a open circuit, and we need to find the open circuit voltage across these two terminals, right? So and further here, this is the circuit to find the open circuit voltage. So here where we need to find, which means here the VOC is nothing but the voltage across the terminal A and B, which means the voltage across these two, not A and B exactly, across the X and Y. So which means the voltage across the X and Y terminals is nothing but the voltage drop across the 1 ohm resistor plus here already the voltage drop here it is which is 6 volts. So if you add these two, then we will get the voltage across the X and Y, which is VOC. So for that, of course, there are many procedures that we can follow, the basic network reduction techniques. So either we can apply the simply the loop analysis or the nodal analysis, okay, because here only one node is there and the two loops are there, and also we can apply the current division rule. So here I am going to apply the current division rule, okay. Same like in the previous class we have discussed, okay, any one of the technique that we can apply. So for that here let us consider here the total current flowing through here it is, let us consider I, and the current flowing through this particular circuit is what is that, I2, and the current flowing through this is I1, okay. So here what we need to find, we need to find the current flowing through I2, which means here these two are in series, so the same I2 will flow through this 1 ohm resistor also. So as we know, according to the current division rule here, I2 is equal to the total current I into the total current I into what is the opposite resistor here? The opposite resistor here it is 2. 2 by the total resistance here it is 2 plus 5 plus 1, because here this is the total resistance, because 5 and 1 are in series already. So now what we need to find here, first of all we should find the value of I. We don't know the value of I, here it is. If you know the value of I, then it is very easy to find the I2 value, right? Then here then if you know the I2 value here, okay, then the voltage across V1 ohm resistor, which is equal, okay, or VAB, which is equal 1 into I2, so that we go know AB value. Then here VOC is equal to here VAB plus here the 6 volts, then you will get the value of VOC. So for that we need to find first VAB, then after that if you want to find VAB, then you need to find I2. If you want I2, then you need to find I. So that's why now we are going to find the value of I, the total current I. So here the total current I is equal to V by the total voltage, here it is V by the total resistance. Okay, so first of all we need to find the total resistance. So okay, directly here I am writing. So here V is 4 by here the total resistance, that here it is the 5 plus 1 are in series. Okay, so R, first let me find the total resistance R total, then we can substitute here R total, which is equal to, so here these 5 and 1 are in series, are in series, so 5 plus 1, and this combination is parallel with this 2 ohms resistor. Okay, and this total is again in series with the this 1 ohm resistor. Okay, this 1 ohm resistor, because here these two, okay, and this is the 1 ohm resistor. So then the R total value here it is, if you substitute all these values, then you will get here the R total value is 5 by 2. Then if you substitute I is equal to V by V is, here it is, V is 4 volts, 4 by 5 by 2, which is equal to 8 by 5 amperes, right? Then substitute here this I value here, so that I2 is equal to 8 by 5, 8 by 5 into 2 by 2 plus 5 plus 1. Then you will get the value of I2, here it is 2 by 5 amperes. This is the value of I2. Then here VOC, which is equal to VAB. So here VAB is I2 into 1, so which is 2 by 5 into 1 plus here 6 volts. So then VOC, which is equal to 32 by 5, because 5 into 6 30, 30 plus 2 32 by 5 volts. This is VOC. Now this is the value of VOC, right? So next, now we got the value of VOC. Now we need to find the load resistance. So the load resistance is nothing but R Thevenin is equal to R load. So for that, here in the given circuit, okay, so where we need to find the R Thevenins, we should find the R Thevenins again across these load terminals. Okay, across these load terminals, across these load terminals. Okay, and in that case we need to replace all the voltage sources as a short circuit and the current sources as the open circuit. But anyway, here we are having only the voltage sources, so that's why then this is the R Thevenin's equivalent circuit. So here then find the equivalent resistance across these two terminals X and Y. Okay, so which is R Thevenin's. So as we know here, the 1 ohm is in series with not series, in parallel. So here R Thevenin's, which is equal to 1 is in parallel with these 2 ohms, and this combination is in series with the 5 ohms, and this total combination is again in parallel with the 1 ohm. Okay, so this is the R Thevenin's. Then the value of the R Thevenin's, here it is, or in another words here 1 into 2 by 1 plus 2 plus 5 okay, plus 5, and this total combination is in parallel with this 1 ohm resistor. Then the total value of the R Thevenin's here it is 0.85 ohms. If you simplify this, then the total resistance that we will get is here 0.85 ohms, right? So according to the maximum power transfer theorem, okay, so according to the condition, according to the condition given in the problem, so here R Thevenin's which is equal to R which is equal to 0.85 ohms. So now we got the first answer, which is R, the load resistance R is equal to 0.85. Then now we need to find the maximum power P maximum. So as we know, P maximum which is equal to VOC square by 4 into R. So VOC now we have calculated, which is 32 by 5. So 32 by 5 whole square by 4 into here R is 0.85, then which is equal to 12 watts. Then here R is equal to 0.85 ohms. Okay. And P maximum which is equal to 12 watts. So this is the answer for the given problem. Right? Okay. Then we will go for the next problem. So here the problems are like just I'm trying to improve little complexity. Okay. Because the first problem, that's why here it is very simple problem. So in the next case, we are considered one voltage source and one current source. Okay. Because in the previous case only two voltage sources are there. So in this problem, we are considering one voltage source and one current source, right? Okay. Fine. So in this given problem, what should be the value of R such that the maximum power transfer can takes place from the rest of the network to R in the below figure, and also obtain the amount of the power. So here also the problem is same. Like first we need to find what is the value of the R, okay, when the maximum power is takes place at a particular resistance R. Okay, then what is that maximum power transfer to that a particular resistor? Okay, so that's what here we need to find. So R and P maximum that we need to find in the given problem, right? So again here also the same way, like because first here R is equal to R Thevenin's. This is the first case, and P maximum is equal to VOC square by 4 into R. So we need to find here the VOC, okay, and R Thevenin's. Then if you find these two, then you can find because R Thevenin's is equal to R, so that we can find the value of the load resistance, and as well as the amount of the power, the maximum power is through that particular load. Okay. Then the same procedure here. First we need to what is that, find the open circuit voltage, so that here we are applying, I mean we are just replacing this load resistance as an open circuit voltage, here VOC. Then we need to find the voltage across these two terminals, right? So first we are going to find the VOC. Okay. So here VOC is nothing but the voltage across these two terminals, X and Y. Okay. So which means again here also the voltage across these two terminals are VOC. Okay. Which is equal to VXY. Okay. So VXY which is equal to here the voltage VAB. Okay. So VAB and minus, okay, because here as you can see the current will flow from high potential to low potential. So here it is flowing from this way, but here it is minus to plus. So that's why we should consider, okay, what is the direction of the suppose if it is VOC plus and minus. Okay, then if you apply the loop analysis here, then the loop analysis that you will get here, it is of course here minus 2 plus, so that's why here it is minus 10, okay, and plus 2 minus, here it is plus VOC, and here it is plus which is the VAB, the voltage across the 5 ohms is VAB. So VAB which is equal to 0, right? So then VOC which is equal to here VAB minus 10. Okay. Then how to find VOC here? First we need to find the VAB value. Okay, so how to find the VAB here? VAB is, let us consider here the current flowing through here, it is I. Then VAB is equal to 5 into I. Okay, so first we need to find I. Then I means the total current which is flowing through this. Okay, so here you may get doubt like, I mean, what about this 2 ohms resistor? So because here this 2 ohms resistor is connected to the open circuit, so that's why the current flowing through 2 ohms resistor is 0. So that's why we should neglect the 2 ohms resistor, right? Because if there is a current, then only we will get the voltage drop across these 2 ohms resistor. But there is no current because the current flowing through this open circuit is 0. So that's why here the voltage drop across this also 0. So that's why we will neglect this 2 ohms resistor. So that's why here, if you apply, I mean, the VOC or VXY is nothing but the voltage across this 5 ohms resistor and plus this voltage source which is connected across these X and Y terminals, right? So then first we need to find I is equal to, I is nothing but the total current flowing through this one. So I is equal to here V by R 24 by 10 plus 5. Okay. So which is nothing but here 1.6 amperes. Okay. Then here substitute here VAB. So VAB which is equal to 5 into 1.6. Okay. So 5 into 1.6 which is equal to 8 ohms. Right. Then 8 volts. Then if you substitute all these values here, okay, then here VOC which is equal to, here VAB is equal to, sorry, here 10 minus VAB, not VAB minus 10. So 10 minus VAB. So here 10 minus VAB is 8. Okay. Then here you will get VOC which is equal to 2 volts. So this is the procedure to find the VOC. Okay. Then now we are going to find R Thevenins. Okay. So R Thevenins here the same across these two terminals. We need to find the value of the R Thevenins. Okay. So then here the voltage sources here. This voltage source should be replaced with short circuit, and this voltage source should be replaced with the short circuit. Okay. That's what here we have done. This is and this one. So here then these 10 ohms and 5 ohms are in series. I mean in parallel. Okay. So here 10 into R Thevenins which is equal to 10 into 5 by 10 plus 5 plus 2. Okay. Then the value of R Thevenins here it is 5.33 ohms. Right. Then now here R Thevenins. So which means here according to maximum power transfer theorem, so R Thevenins which is equal to R which is equal to 5.33 ohms. Right. Now we need to find what is the maximum power flowing through that particular load resistor. So here we know that P maximum which is equal to VOC square by 4 into R. Then substitute the values here. So VOC here it is 5.33 whole square by here 4 into here R, no sorry, this VOC not this one. So VOC here it is 2 volts. Okay, so 2 into 4, 2 whole square by 4 into 5.33. So then here the maximum value here it is 188 milliwatts. So then here P maximum which is equal to 188 not mega milliwatts. Okay, milliwatts. Right. So this is how we can find the value of the P maximum. Right. Then going to the third problem. So here third problem, this is also a very simple problem. So in this case, again, first we need to find the load resistance value R, okay, and as well as the maximum power flowing through this load resistance R. So for that, first we need to find the VOC. So to find the VOC, what we need to do, just to replace the load resistance as a open circuit, and we need to find the voltage across this open circuit, right? So here it is really very simple. So which means here VOC is nothing but the voltage across the terminals A and B, which is nothing but what is that? Suppose if the current is then 10 into I. This is VOC. So which means first we need to find I. So I is equal to here the total current flowing through this particular circuit. So V which is equal to 50 by R, which is what is that, 1 plus 1 plus 3 plus 10. So which is equal to 50 by 50 by 15 amperes, right? Then here VOC, which is equal to here 10 into 50 by 15. So here it is 500 by 15, which is VOC. So which is 33.33 volts. But here, as you can see, the VAB that we are considered here, it is plus and here it is minus. But here actually VOC, here it is plus and here it is minus. So which means here VOC, which is equal to minus VAB. So which means here VAB is 33.33. So which means here VOC, here it is minus 33.33 volts, because here plus 2 minus, so that's why here the current direction is like this. So that's why here also the voltage here it is plus and minus. Okay, so that's what, but actually VOC here it is plus and minus, so the polarities are reverse. So that's why here the VOC here it is minus 33.33 volts, not the 33.33 volts, because here this from B to A, this is actually okay. So that's why here, which means here this is not VAB even, this is VBA. Exactly, here it is VBA. So which means here VBA is equal to minus VAB. Okay, no, VAB is equal to minus VBA. So VAB is equal to minus VBA. That's why here it is minus 33.33 volts. Then now we need to find the R Thevenin's value. So for that R Thevenin's, we need to just replace the voltage source as a short circuit, because here we are having only one voltage source. So which means here the R, what is the Thevenin's, which is equal, here these 1 plus 1 plus 3 are in series, and this combination is in parallel with this 10 ohms, and this total combination is in series with this 5 ohms, right? So that here the value of the R Thevenin's that you will get is 8.33 ohms. 8.33 ohms. So this is R Thevenin's. So again, according to the maximum power transfer theorem, so here this R Thevenin's, which is equal to R, which is equal to 8.33 ohms, right? Then now we need to find the what is the maximum power flowing through this particular circuit. So then here P maximum, which is equal to VOC square by 4 into R. So here VOC, here it is minus 33.3 whole square by 4 into here R is 8.33. Then if you calculate and if you simplify this, then you will get the maximum power, here it is again 33.34 watts, 33.34 watts. So here then the P maximum, which is equal to 33.34 watts. So this is how we can find or we can apply the maximum power transfer theorem to find the load, the value of the load resistance, as well as the maximum power flowing through that particular load resistance, right? Then coming to the problem 4. Okay, so here it is a little what is that, not complicated actually, but we should know the the exact methodology to find the voltage across the X and Y terminals, right? So here also the same thing. First we need to find the load resistance, okay, the value of the load resistance, and then after that we need to find what is the maximum power flowing through that load resistance, right? So first here let us write the VOC. So first let us find the voltage VOC, open circuit voltage across these two terminals. Okay, VOC. So here the VOC is nothing but VXY. So here VXY is nothing but, here we should find the voltage across what is that, the 3 ohms resistor. Okay, so which means here the voltage across the 3 ohms resistor, the VXY or VOC is nothing but. Then If you know the current flowing through the 3 ohms resistor, then it is very easy to find the voltage across these 3 ohms resistor. There are two ways to find the voltage across 3 ohms resistor. So one thing is, here as you can see, uh, this current source can be transferred into the voltage source. Okay, so let me draw here the circuit. So this is this one, plus and minus. Okay, and here it is, let us consider again the same 1 ohm. Okay, so here in this way it is flowing, so that's why here it is also plus and minus. Okay, and then same, the internal resistance is there, and here 2 ohms is there, and here it is 3 ohms is there, right? So here it is 15 volts, and here it is 1 ohm, and here it is 5 ohms, and here it is 3 ohms, right? So here this current source can be transferred into V is equal to I into R. So here I is 5 and R is 10, so here it is 50. So which means here it is 50 volts, and here it is what is that, the value here it is 10, again here it is 10 ohms. Okay, so you just apply simply the loop analysis. Okay, then here I is equal to, what is that, the total current I is equal to V. So here V is okay, actually here it is, as you can see here, positive to negative, positive to negative. So 50 plus 15 by here 1 plus 10 plus 5 plus 3. Okay, then if you simplify, then you will get here I is equal to the value of the I here it is, that you will get here it is equal to 3.1. Okay, so 55 by here 10, 15, and 18, 19. Okay, so then here the value of I that you will get is equal to 3.1 ampere. Okay, this is the one way that you can find, and another way here it is, instead of this, okay, you no need to convert the voltage source into what is that, the current source into voltage source. Okay, so directly you can solve by using a nodal analysis, because here we are having only one node that we can consider. Okay, so the node voltage here it is, let us consider here the voltage at this particular node is equal to V. Then here if you write the node voltage, so V minus 15 by here the resistance is 1, or just apply the, what is that, the KCL at that particular node. So here plus, and again here 3 plus 2 5, so V minus, okay, because here potential is 0, so 0, V minus 0 by the voltage is 5. Okay, and plus here one more resistor is there, so V by V minus 0 by 10, which is equal, here the 5 amperes current is there. Okay, which means here these all are the leaving currents, and this is the entering current. Then if you simplify this, then you will get here V is equal to 15.4 volts, right? Then but we need to find the current flowing through this 3 ohms resistor. Okay, so the current flowing through, which means here these two are in series. Okay, 2 ohms and 3 ohms are same, so which means this 5 ohms resistor. So here then let us consider, here it is I2. So here I2 is equal to the potential here V is 15.4 by, and 2 plus 3, here it is 5. Then here the I2 is equal to, again you will get the 3.1 ampere. Okay, so in the previous case also we got the same value, and in this case also we got the same value, right? Now we need to find the voltage across the 3 ohms resistor, which is equal to because here again the 5 ohms is connected to open circuit, so I mean the current flowing through these 5 ohms is 0, so that's why we neglect the voltage drop across the 5 ohms is also 0, so that's why here V 3 ohms is equal to 3.1 into 3, so which is equal to 9.3 volts. So here VOC, which is nothing but 9.3 volts. This is how we can find the VOC. So that's what I told. I mean, I told you, like there is no criteria to follow this particular basic network reduction technique only. So we can follow any one of the basic reduction technique according to our convenience. Then we can find the voltage across these two terminals, right? Then of course now what we need to do to find the R Thevenin. So we need to replace this as a short circuit, and this is a open circuit. Okay, so that's what here. This is the the actual equivalent circuit. Then here again it is easy. This 1 ohm and 10 ohms are in parallel. Okay, and this parallel combination is in series with the 2 ohms, and this total combination is again in parallel with the 3 ohms, and this total combination is again in series with the 5 ohms. Okay, so here, which means here 1 into 10 by 1 plus 10. Okay, 1 plus 10, 1 plus 10 plus this 2. Okay, plus this 2, and this combination is in series in parallel with this 3, so that's why 3 by here again 1 plus 10 by 1 into 10 by 1 plus 10 plus 2 plus 3, and this total combination is in series with this 5 ohms, so that's why here it is plus 5, so which is equal to here 421 by 65 ohms. Okay, so here, which means this 1 ohm and this 10 ohms are in parallel. Okay, so that's why here 1 into 10 by 1 plus 10, and this total combination is in series with the 2 ohms, so that's why here 1 into 10 by 1 plus 10 plus 2, and this total combination is again in parallel with the 3 ohms, so that's why here into 3 by plus 3, and this total combination is in series with the 5 ohms, so that's why plus 5. Okay, then now we need to find the maximum power which is flowing through this particular, let us see here. Yeah, so what is the amount of the maximum power? Then here the maximum power P maximum, again the same equation, which is equal to VOC square by R Thevenin's. Okay, so here VOC, that is 9.3 whole square by here what is that, R Thevenin's, here it is 421 by 65. Then if you simplify, then you will get the value of the P maximum, right? So this is how we can find the P maximum, right? Then coming to the next problem here. Okay, so in this problem also the same thing, we need to find the what is the load resistance, and as well as the what is the maximum power flowing through the load resistance. And here also this is very simple. Okay, so again here the VOC, okay, which is nothing but the voltage across these two terminals. Okay, so plus and minus and plus and minus, so that's why here then VOC, okay, so which is equal to 10 plus, let us consider here it is A and B, then VAB. So first we need to find the VAB. Okay, VAB is equal to VAB is nothing but, let us consider here the current is I. So I into 2. So first we need to find I, then I is equal to, here it is 20 by what is that, not 20 and plus and minus. Okay, so here it is 20 plus 6 by here 10 plus 5 plus 2, then the value of the high, here it is 14 by, okay, 17. Oh, minus 2 plus, and here plus 2 minus. So here 20 minus 6. This is not 20 plus 6. 20 minus 6, because here it is the is minus 2 plus and plus 2 minus. So that's why here it is 14 by 17. This is the value of I. Then here VAB, which is equal to, here I is equal to what we got the value, here it is 14 by 17. Okay, into 2. So which is equal to 11.65, not 11 point. Okay, so 1.65. Okay, so then this is VAB. Okay, let us consider here it is like this. Then VOC, which is equal to here 10 plus, okay, so not I is equal to, here it is 14 by 17. Yes, 10 plus, so here 14 by 17 into 2. So then here it is finally, here it is 11.65 volts. So here VOC is equal to 11.65 volts. Right, then finally R Thevenin, here it is very simple, 10 plus 5, 15, and so 15 into 2 by here 15 plus 2, so which is R Thevenin's. Okay, so here it is, which is equal to 1.765 ohms. Then again the P maximum, which is equal, because here it is, which is nothing but the R value. So VOC square by 4 into R. So which is equal to VOC, here it is 11.65, 11.65 whole square by 4 into, here R is equal to, what is the value of R? 1.765. Then here the P maximum is equal to 19.22 watts. This is how we can find the value of the R thevenins or the load resistance R and the maximum power flowing through that particular load resistance R, right? Then now the fifth problem. Okay. So here the fifth problem, as you can see here, it is totally different, the circuit from the previous circuit what we have discussed. Okay. Of course, here this is also very simple, but only one key point is there. Okay, if you are able to identify that key point, then it is very easy to solve this particular problem, right? So in this problem also, again, we need to find the total, I mean, the load resistance R value, as well as the total the power, the maximum power transfer to that particular load resistance. Of course, again, we need to find the voltage across these X and Y terminals for this particular case. Okay, so the voltage across X and Y terminals. So here the voltage across X and Y terminals is nothing but which means here let us consider, if you let us consider here it is a loop. Okay, so then the potential, okay, across X and the potential across Y. Then here as you can see, the loop E, here it is. Okay, so minus Vx, because here plus to minus, plus Voc, and plus here Vy, which is equal to 0, which is equal to 0. So that's why first we need to find Vx and Vy. So simply we can apply the nodal analysis, okay, to find the voltage across these two terminals. Okay, so first let us find Vx. Okay, so here it is Vx. Okay, so fine, yeah, Vx by 5. Okay, and Vx by 5 plus here Vx by 2. Okay, and which is equal to here 5 amperes. Okay, then here 7 Vx sorry, so 7 Vx by 10, which is equal to 5. Okay, then from this we can find here Vx is equal to what is that, 50 by 7, so which is 7.14, something like that. So here 7.14 volts, here it is Vx, right? Then similar way we can write the Vy. Okay, so here Vy, here it is, then let me write here, okay, for that Vy. So directly we can write here Vy, which is equal to Vy. So as you can see here, Vy by 4. Okay, or this is nothing but here it is, the current is flowing through, here it is 2 amperes. Okay, so that's why Vy is equal to or Vy by 4 is equal to here or minus, because minus Vy let us consider. Okay, so which is equal to 2. Okay, then here Vy, which is equal to 4 into 2, here it is minus 8 volts. This is Vy. Okay, Vy is equal to minus 8 volts, right? Then substitute in this equation. So here Vx is equal to minus 7.44, minus 7.44. Okay, let us, here it is like that. So Voc is equal to here Vx minus Vy. So here Vx is equal to 7.44 minus Vy is equal to minus 8 volts. Okay, so minus 8, then it is 15.14 volts. So this is nothing but Voc is equal to 15.14 volts. Okay, so this is how we can find the value of the open circuit voltage, right? Then of course next we need to find R Thevenin. So R Thevenins, just we need to open circuit this one and this one. So which means here it is open circuit. Okay, so then the total value of the R Thevenins, here it is this 2. Of course this is connected to the connected to open circuit, so that's why here this will get 0. So here 5 and 2 are in parallel, and this parallel combination is in series with the 2. So which means here R Thevenins, which is equal to 5 into 2 by 5 plus 2 and plus 4. So here the value of R Thevenins, here it is 5.43 volts. Then which is nothing but the R. Okay. Then here the P maximum, which is equal to VOC square by 4 into R. So here VOC that we got is 15.4. So 15.4, I mean 15.4 whole square by 4 into here R is 5.43. Then finally you will get the value 10.96 watts here, which is the P maximum. Right? Okay. Then now we are going to take another problem. Okay, so in this case now we are having the 3 loops. Okay, before we are having only the problems that we have discussed about 2 loops. Okay, of course some are having the 3 loops also, but the case is different. So here first we need to find the open circuit voltage. So here it is very simple again. So the voltage across VOC is nothing but the voltage or VOC, okay, which is nothing but VOC, which is nothing but the voltage across plus minus. So that's why then V 5 ohms plus this 50 volts. Okay, this is VOC, right? So plus minus, yeah. Okay, then first of all we need to find the voltage across the 5 ohms resistor. So for that we need to know the current flowing through this particular loop 2. Okay, so for that we need to write the loop equations. Okay, then from that we can find the so first loop equation, it is very easy. So 20 I1 plus here 2 into I1 minus I2, which is equal to 20. This is equation number 1. Similarly for loop 2, here it is, let us start with 10. So 10 I2 plus here 5 I2 plus here 2 into I2 minus I1, which is equal to 0. This is equation number 2. Okay. So here by solving 1 and 2, then we will get the value of I1 and I2. Okay. So we need only I2 value. So that's why I'm just simply writing the value of I2. Here it is 0.108 amperes, right? Then what is the voltage across 5 ohms resistor, which is equal to I2 into the value of 5 ohms is 5. So here 0.108 into 5. So here it is 0. Something 0.54. Okay. Volts. Okay, then here VOC, which is equal to let us consider A. Okay, according to equation A, here V5 volts is 0.54 plus 50, so which is nothing but here 50.54 volts. This is VOC. See how simple it is, right? But the thing is, it is very important to know like what is mean by the VOC. Okay, so sometimes you may neglect that VOC is nothing but the voltage across the 5 ohms resistor only, but it is not like that. It is the VOC is, so which means you have to identify, okay, so how many voltage drops that we will get across these two terminals. Okay, one voltage drop that they have already given 50 volts, the another voltage drop here it is the voltage drop across the 5 ohms resistor. So that's why here then the total voltage drop across these VOC terminals, here it is the voltage drop already the voltage drop 50 plus the voltage drop across the 5 ohms resistor. That is how it is very important point here. After that to finding the voltage across these 5 ohms is very easy because the normal procedure are very basic procedure that we have applied. Then R Thevenins. Okay, so again because here these two are in these two are in parallel and this combination is series with this and the total combination is in parallel with this. Okay, so that is how we can find the R Thevenins value. So here then the R Thevenins value, here it is R in just simply I'm writing here 20 into 2 by 20 plus 2, right? So and this combination is in series with this 2 ohms resistor. Okay, sorry, this combination is in parallel series with the 10 ohms resistor. So here plus 10, right? Then this total combination is in parallel with the 5 ohms. So that's why 10 into 5 by 20 into 2 by 20 plus 2 plus 10 plus 5. So then which is nothing but the R Thevenins. Then the value of the R Thevenins here it is 3.5 ohms. Right? Then again find the P maximum. Then P maximum which is equal to VOC square by 4 into R. Then here VOC, the value of the VOC that we got is 50.54. So 50.54 by here 4 into here R value is 3.5. Then we will get finally the value is 182.44 watts. This is the P maximum. So as you can see, because till now we have seen 7 problems. In all these 7 problems, the key element is okay. So to identify the open circuit voltage terminals, okay. Then how to find the VOC is the key element here. If you are able to find the VOC, okay, then it is very easy to apply other things, because the R Thevenins, okay, as we know, because we have solved many problems based on these equivalent resistance. Okay, so how to identify the series combination and parallel combination. So then it is very easy. That is very basic problems to find the equivalent resistance. Okay, but the thing is, okay, so how to find the VOC, because here we have seen 7 different cases. In the 7 different cases, the VOC is different, because it is not just like across only one resistor, or not just like across only one what is that voltage source, or because here sometimes based on the terminal what is that the polarities. Okay, so plus minus and minus plus also sometimes what is that the based on the polarity, sometimes we are just adding the potential across these 2 points, and sometimes we are just subtracting the potential across these 2 points. Okay, so that's why here it is very important to know the VOC, okay, or the procedure to find the open circuit voltage, right? Then now finally here we are going to solve one more problem. Again we need to find the voltage across these VOC, okay, I mean the terminals of these two. So here one thing, that common point that you can see, whenever there you can find more number of current sources, then you better to go for the nodal analysis. Okay, instead of the loop analysis or mesh analysis, it is better to go for the nodal analysis. Okay, so that it is very easy to find the potential across the or the open circuit voltage, right? So here the potential across these VOC is nothing but, okay, the potential across VOC is nothing but, of course here the current flowing through 5 amperes is there, so which is nothing but the same current here this is the same current which is flowing through this 1 ohm resistor also. Okay, then here the potential across these two is nothing, VOC is nothing but, okay, so then for that let us find here the nodal analysis. Okay, so here this is VA, okay, and here it is B. Okay, so first let us try to find the here VA, so I mean or the V. Okay, so which is nothing but V minus. So here let us consider here this is the voltage across 1 ohm drop. So that's why here V1 ohm let us consider by here it is what is that 10. Okay, because this way we are finding. Okay, so 10 the total resistance, plus here it is V minus here 20 is there, so 20 by here 2 ohms is there, so 2, and plus, okay, so already here it is VOC is there, okay, at this particular point here it is VOC, so that's why here I am just writing V minus VOC by 5. Okay, V minus VOC by 5, okay, which is equal to here actually just 2 amperes. Okay, so which is equal to actually then again here V2, this particular VOC point here it is the 2 amperes, so that's why let us consider 2, right? Then if you simplify this, then you will get finally, okay, 0.8 V minus 0.2 VOC, which is equal to 15. So let us consider this is equation number 1. Okay, if you solve this, then you will get this one. Then again, here this is one more terminal B is there. Okay, with respect to the B, okay, then again apply what is that? The same nodal analysis. Okay, so here VOC at B, because this terminal is same, so that's why VOC minus here V by 5 ohms, 5 ohms. Okay, and here, because here the same way, here VOC to this particular, again this through this terminal, here it is 2 amperes. Okay, 2, which is equal to here again VOC from this to this particular point, here it is 5 amperes. So that's why, because opposite direction, so here it is 5. Then if you simplify this, then you will get the equation 2 is 0.2 into VOC, 0.2 into VOC minus 0.2 into V is equal to 3. This is equation number 2. So by solving equation number 2, 1 and 2, by solving 1 and 2, okay, so then here VOC, which is equal to 45 volts, VOC which is equal to 45 volts. So here the key thing is, okay, let me explain once again, okay, how we have written these two equations. Okay, so first equation, here V minus V1 volt. Okay, here V minus, here it is V1 volt. So V1 means here 1 volt means here already current, you know, so which means here it is actually the 5 volts here. Okay, so instead of 1 here we can substitute directly the 5. Okay, because here 1 into, because V is equal to I into R, so here I is equal to the same 5 amperes is flowing, so 5 into 1, so that's why here it is 5, right? So that's why directly instead of this you can write it as a 5 also. There is no issues, right? Then the second, this is one case. Okay, V1 minus 5 by 10, and then again 2 ohms is there, so V1 minus 20 by 2. Okay, and then another one here V1, okay, minus VOC, because this is another point. Okay, VOC point, this VOC point is VOC by 5, which is equal to here the 2 amp. That this is not 20, this is 2 amperes. This is first equation. And second equation again, again from with respect to this particular point. Okay, VOC, which is also called connected to V, I mean the point V. Here VOC and VB point is same. So here VOC, okay, VOC minus V by 5, so VOC minus V by 5 plus, okay, this is also 2 amperes plus 2 amperes, okay, and which is equal to 5. If you simplify this, then you will get the equation number 2, and by solving 1 and 2 we will get the VOC, right? So this is how we can find the open circuit voltage. Then now R Thevenin's, anyway here we are having the 2 voltage sources, so this one is get 0, okay. Then here these two are in a parallel and the other combination is in series. So then R Thevenin's, which is equal to 10 into 2 by 10 plus 2, and this combination is in series with this 1 ohm and the 5 ohm. Then you will get the finally R Thevenin's is equal to 7.67 ohms. Then the P maximum, which is equal to VOC square by 4 into R. So which is equal VOC, we got 45. So here it is 45 by, okay, and 4 into here R is 7.67. Then the P maximum value, which is equal to 66 watts. So this is how we can find the maximum power transfer theorem. I mean, by applying the maximum power transfer theorem, we can find the value of the unknown load resistance value, and as well as the maximum power transfer to the particular load resistance, right? So in the next class, we will discuss numerical problems on another theorem. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.